Hello and welcome to another video. I thought I'd do something a bit different tonight, just because this came out the other day and lots of students were asking me about different questions, and I thought I'd do the last two. I've only figured these two out just now, basically, and so I'll quickly go through them. Actually, this one somebody asked me in the lesson about this one, and I managed to totally do Pythagoras' theorem wrong in the first step. Uh, Disappointment, let's just put it like that. But anyway. I think these are the answers to these two, so let's have a go at them. 24. This is my thinking basically on this one. Uh, Firstly, you could kind of cheat and kind of give P and Q actual numbers here, like 2 and 3 or something like that, and it will probably wind up giving you the right answer, I'm guessing, unless they've thought carefully and made sure there's a stitch up in there. But you could, if you just pick relatively 2 and 5 or something like that, it might make the question slightly easier. But what I'm going to do will apply for whatever numbers of P and Q you pick, if you did want to do that. I'm just thinking basically, well, what you might think first when it says maximum possible value is, oh, differentiate or something like that. And it's certainly possible to differentiate that and this expression implicitly, for example. But of course, you're actually looking for integers here. That's a big kind of deal. And really, we don't use differentiation when there's integer possibilities because the integer idea firstly narrows down possibilities and normally implies there's another way. Also, this is a math challenge, and the math challenge you never need differentiation on any of the questions ever. They're really good at setting questions which don't actually involve any A-level content really. In the senior math challenge, where obviously pretty much everybody's doing A-level, but it's really cleverly done. So yeah, so how can we do this? Well, I'm thinking draw a graph. That's what I'm thinking. Like it would be lovely to draw a graph, get an idea, isolate y, and draw a graph. So xy minus qy is px, and then if I can isolate y by making that x minus q, I can quickly get the graph, which is y equals px over x minus q. Okay, that's not too difficult to draw because let's actually draw this out nicely. Sorry. Let's do it. I hope this is going to be a nice enough diagram to show you what I'm talking about. Okay, we've got an asymptote on the bottom at x equals q. And by all means, pause the video here if you think I've given you enough of a hint now. um, Now, where's the vertical asymptote going to be? Well, let's let x tend to infinity. Just pretend x is like a million or a billion. Like, q is basically going to become insignificant because you can always choose x to be sufficiently larger than q. And so really you can ignore minus q on the bottom and just do px divided by x, which is p. In other words, there's going to be an asymptote, vertical asymptote at y equals p. You also know things like it's going to go through 0, 0, because when x is 0, y is going to be 0 there. And so the curve is going to look something like this. It's going to be like a y equals 1 over x graph, basically translated. That's what all these graphs of this type look like, actually. Especially rational functions. If you've done much work on rational functions, it really helps you sketch graphs. And sketching graphs is a really useful technique. So why does it help me in this question? Well, it's saying when y takes its maximum possible value, well, naturally we want that to be up here in this graph. And you might think initially, well, surely the maximum possible value of y is unbounded, because it's just going up and up and up. Yeah, like forever up here. Well, no, because y is constrained to be an integer. So there will be like a value, if you think of the lattice of integer points here, um, I should put that on that line really because p is supposed to be an integer. So 1 second. If you think about the lattice of points, can I do this in a different color? It'd be quite nice to use a different color. I hope that if you can imagine, these are all integer points, yeah, on the diagram. And this is quite hard to kind of think about. There is going to be a final integer point there between which the curve will just get really, 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 really high. And so it's that integer point I want to talk about because that at that integer point, well, where is it? Well, all of these points have an x component of q. Yeah, that's their, their x value of their which will be an integer, because remember x, y, p, and q are all integers. And so the next one will be q plus 1. And at that point, you'll have maximized y, because otherwise you'll break the condition that they're all integers. Because, yeah, sure, y up here can be higher and higher and higher, but x will not be an integer between there and there. And so you're just making y higher and higher and higher. So the next integer point for y is going to be when x is q plus 1. And that's going to be over here. Well, how can we find that? We can plug this in here. Basically, we've cracked the problem now from like a crafty diagram, and we can do it, because if x is q plus 1, what is y going to be? Well, y is going to be, you could go back to the start really to work this out, but p times q plus 1 over, you're going to get q plus 1 minus 1 on the bottom, minus q on the bottom, which leaves 1. And so y is p times q plus 1. Now, what's it looking for? It's looking for the what's equal to y minus x. Well, y minus x is therefore p times q plus 1 minus a q plus 1. Factorize that, and you get q plus 1. They've got a common factor of q plus 1, and then p minus 1. And so I think the answer is C. That's my thinking anyway. Let me know if I made a mistake, or hang on, I've just circled something which actually isn't there. That's not C. You see, this is what makes me laugh when I try and do these questions. It's D. I'll work it out correctly, and then I circle the wrong one. Have you found yourself doing that? Like, check your answers, people. Like, all that hard work to get the answer wrong. Okay, right, let's try and do 25. I'd love to draw this diagram out for you on GeoGebra. It's, this kind of like 3D thinking is really quite tough, and a good diagram really, really helps. I did use this one though when I worked this out. So yeah, let me show you what I did. So first things first, like, volume of like this weird shape. It's not a prism, is it? Like, there's no cross-sectional, like uniform cross-section like you can take across that shape. So, you can't use that. What are you going to use? Well, the only thing which popped into my head is like, this is basically a tetrahedron, like that's what it is. And anything which is pointy at the top, I don't know how to put this, anything which tapers to the top, like a tetrahedron, or a pyramid, a square-based pyramid. You could do it with this, or a cone. All of these shapes have something in common when you work out their volume. You could have a hexagonal pyramid, like any shape like this. I hope you can see the point I'm making here. Any shape which tapers to the top like that, which kind of has, if you like, I'm trying to think of the way to put this, but when you take the cross section, it's just a scale factor reduction of the base. Yeah, when you take the cross section anywhere in these shapes, like that's what's kind of important. You get a similar shape with the cross-sectional cut. Well, all of these have the same volume formula, which is a third times base times height, perp height. So that's the principle I'm going to use here. Yeah, I need the perpendicular height of this. That's what I really, really, really need. I can probably get away with working out the base area on that kind of description, but the tough bit's going to be working out the perpendicular height. But all of these shapes, yeah, it's worth knowing that all of those shapes have volume equals a third times base times perp height. So okay, let's have a go at this question now, knowing that fact. And by all means, pause the video now if you really think, oh, if that's the secret, I want to have a go. Go for it, yeah. Don't don't watch this first. Have a go at it first yourself. You don't need my ridiculous explanations to get you through this. You can do it. Right. Okay. So what is it? I think every single triangle is congruent, and it's 10 by 10 by 4. So that's 10. That's 10. That's 4, etc., etc., etc. But what I'm really interested in working out is, if I can dot this down to here, that bit right in the middle, yeah, it's right in the middle of there. I need that height, yeah, because then I can do a third times by the base area times by the height. Now, how can I do that? Well, it looks like a futile quest at first. It really does, because you're going to have to find that all the way up from there up to there. Yeah. Now you can start making other right angled triangles, and you should do when you get these kind of 3D trig problems. That's actually not that bad. Sorry, I'm just going to flatter myself about how good that diagram is. I'm well chuffed with that. That's good. Okay, so right. How can we do this? Let's put this as 2 and 2. Yeah. Clearly I can actually work out that length right the way up from there to there. Yeah. I can work out that length. That can be obtained. So let's actually work it out. I can work out lots of these lengths actually, because remember there's lots of right angles here. So clearly, let's I tell you what, let's call this M. And let's do MR first. So it's now just a series of Pythagoras' theorem kind of steps, which is obviously fine. So 100 squared minus 2 squared, square rooted, that's root 96. Yeah. Immediately, like the root 23's in the answer should be screaming at you as well, really, at this point, like if you had to guess and you were running out of time. But okay, so I know that's root 96, and I can actually convert that to root 96 is going to be the same as 16 times 6, so it's 4 root 6. Yeah, so you can think of that as 4 root 6, but I think sometimes actually it's handier to think of it as root 96 and do the cancelling at the end. Okay, we've got an A here. Let's call this A and this B. Yeah, I can now set up like some simultaneous equations with Pythagoras on this triangle and this triangle to find A and B, and hopefully link that. Well, if I've got A or if I've got B, I can immediately find H from Pythagoras' theorem. Once I've got that, I'm pretty confident I can find the volume of this shape. So that's my strategy. So I can say A squared plus H squared is 96. I can also say B squared plus H squared is 16. But remember, I've actually got the length of A and B because this also forms a right angled triangle, doesn't it? This SMP one, where A is the hypotenuse, sorry, A plus B is the hypotenuse, and this is 10, and this is 2. So what we can actually say is that A plus B, we've already worked it out. It is root 96. Yeah, A plus B is going to be, oh, yeah, that is yeah, I'm just checking in my head that does make sense. Yes, it's exactly the same middle line. Cool. Okay, so that's what we know here. So we need to solve this by substitution. Just basically subbing it in and solving it. I'm looking, first I eliminated h basically from these two equations. So I had 96 minus a squared equals 16 minus b squared. Looking at those two, and then I kind of used this and thought, well, a is actually root 96 minus b all squared, so I've got 96 minus root 96 minus b, and I'm squaring that, and that equals 16 minus b squared. Sorry, I haven't got much space on the screen here. It's annoying. I've already, I don't want to rub out that lovely diagram, but I'm going to have to. 1 second. Okay, come on, move away. Okay, so naturally now it's just like cranking through the algebra, really, this question. We've got the right idea, if you know what I mean. It's one of those times where you kind of feel, oh, I think I've hit on the right thing here, especially because obviously when you multiply this out, you get 96. You get nice things cancelling. You're going to get 2 root 96b plus a b squared, but I'm kind of happy with that because I've got a minus b squared over here, and after I apply the negative, that's going to cancel. That's going to cancel. That's going to turn into 2 root 96b equals 16. And so divided by 2, 8, b is 8 over root 96 by the look of it. Yeah? Oh, why have I written 89? Okay, so we've worked out what b is, yeah? And we can clearly work out what h is then, and that's what we really want to do here. Like that's the holy grail. So we know that h squared plus b squared, which will be 64 over 96, is going to be equal to 16. So we've got h squared is 16 minus 64 over 96. That surely cancels, doesn't it? 64 over 96. What have we got there? 16's going to both. 4 over 6, 2 over 3. So actually 32 went into both. Yes, quite obviously. My God. So that's 2/3. So this is like 15 and a third. Yeah. Let's write that slightly nicer as 46 over 3. Okay, right. We've got, oh, and that's h squared, sorry, not h. Okay, so we've got to work out the volume. Let's see if we get the right answer. Okay, the volume is going to be equal to a third times base times height. And that equals, let's have a look, a third times by, now with the base, what have we got here? Well, let's use the two right angled triangles here. Let's actually go 2 times, well, 4 times root 96 times by half. Root 96 is 4 root 6 as well. I think I'm going to write it like that. Times by a half, because I'm getting near the end of the question now. Then I've got to times it by the height, which apparently is root 46 over 3. Okay, well, 4 times 4 times a half, that's going to be 8 root 6 over 3. And then I'm timesing that by square root of 46 over 3. Okay, that's going to give me, what's that going to give me? If I take out, are there any square factors in 46? Certainly not, because that's 2 times 23. That's going to give me 8 over 3 times by, I might even call that root 9 down there, actually, just to make things a little bit nicer. I'm just checking. Do you mind if I just turn to my notes? Because I don't remember getting quite this number when I looked at it. Oh dear. What's happened at the end? No, I did get root 46 over 3. Let's just work out the base again. Yeah, a half times 4 times 4 root 6, which is 8 root 6. Yeah, that is over 3, and this is going to be root 46 over 3. I'm confident, actually, I haven't made a mistake. I just had to quickly look at my notes because I was just looking at thinking, what are the options here? What am I actually looking for? I'm pretty sure I ended up with that. Now, 23 and 46. Ah, yeah, because there's a factor of 2 in it. I'm an idiot. Okay, so what have we got here? We've got 8 times. Do the prime factor decomposition, actually. I'm being such a fool. Like, if you write this in its prime factors, and then this one in its prime factors, you see the obvious, like, moves to make, if you know what I mean. Over 3 root 3. Well, look at this. We've got a root 3 on the top, which cancels with that root 3. We've got a 4, which can be square rooted to 2. So we end up with 16 thirds over root 23. God, I'm such an idiot sometimes. But yeah, that is how you do that question, I think. Well, that's how I did that question. So yeah, I hope that was useful. I think these questions on the Maths Challenge are fantastic. I have massive homage to the people who write them. Like, they're brilliant. They always manage to baffle me. And yeah, they're really good fun to do. So yeah, I hope it was useful, and keep up the good work. Bye bye.